Yes, Chemistry Paper 1, May 2019. Question number 1.1. Sodium fluoride contains sodium ions Na plus and F minus ions. They've both got the same electronic configuration. So how's that come about? Well, sodium Na has got 11 protons and 11 electrons. Fluorine's got 9 protons and 9 electrons. So Na plus has lost one, it's got 10 electrons, and F minus has gained one, it's gone from 9 to 10. They've both got 10 electrons, they've got the same electronic configuration. So I've put that here, both atoms have the same number of electrons and the same number of shells, so the same amount of shielding. Normally you'd put that in. The reason I put it in brackets is it's actually not needed. Brackets means it's not wrong to put it, it's correct chemistry, but it's not going to get you any marks. And the reason in this case it's not going to get you any marks is because they've already said that they've got the same electronic configuration, so I'm really repeating what's in the question. However, this is important. Fluorine has less protons than sodium, so it's got an atomic number of 9. Now when it's gained F minus, it's gained an electron and got 10 electrons, but the number of protons hasn't changed. And similarly, Na has got a proton number of 11. Well, when it's lost an electron and gone down to 10 electrons, the number of protons is still 11. So Na has got 11 protons and F has got 9 protons. That's unchanged by the plus and the minus ions. So fluorine has got 2 less protons. It's got 9 protons rather than sodium's 11. Good to put the 2 in to actually name it, but again you don't get any marks. It's got less protons than sodium, so it's got a lower nuclear charge, and therefore it's got weaker attraction. Again, good practice to put outer electrons, because it's the outer electrons that determine the size of it, and so less attraction for the outer electrons having 2 less protons than sodium. Explain in terms of structure and bonding why the melting point of sodium fluoride is high. Well, look, you've got ions. The reason you've got ions is sodium wants to lose 1 electron to fill up its outer shell, and fluorine wants to gain 1 electron to fill up its outer shell. Sodium's in group 1, fluorine's in group 7. So the sodium atom donates an electron to the fluorine atom and becomes an Na plus ion, and the fluorine becomes an F minus ion. And those attract very strongly with something called an ionic bond, sometimes called electrostatic attraction. So because they're oppositely charged ions, they attract very strongly, ionic bonding or electrostatic attraction. They're also held in a regular ionic lattice. That's a good thing to put. It doesn't actually in this case get you any marks, but it's a good thing to put. It means that it's in a stable, regular ionic lattice. Anyway, a large amount of energy is required to break these strong ionic bonds. That's important because that then relates to the melting point and why you need a high melting point, a large amount of energy to be able to break that ionic lattice and turn the solid into a liquid. Name the type of bond formed when HF reacts with H+. Well, what is a H+? A hydrogen atom, before it's gained a plus charge, has got a proton number of 1. It's got 1 proton and 1 electron. Now it's become 1+. It hasn't got any electrons at all. It's just a proton. That's all it is. So how can it form any kind of bond if it's got no electrons? Well, it can form a special kind of covalent bond called a coordinate bond. And normally a covalent bond is where one atom puts 1 electron in and the other atom puts an electron in each, and they've got a shared pair of electrons between them, both wanting to gain electrons. But this H+ has got none to put in there. So what actually happens is it's a covalent bond that's formed when both electrons have come from one of the atoms. So one of the atoms forming the covalent bond has put both electrons in rather than each atom putting 1 in each. And that's come from the F, because it's the F that's bonded to the H's. So the F has put both electrons in to this covalent bond, and it's called a special kind of covalent bond. It's called a dative or coordinate bond, whichever you want to put, whichever you can remember. So what I've got here, SPF minus 6, I've got to do the shape and the name, the shape, and similar for H2F+. So let's do SPF 6 minus. If you find SB, it's in group 5 of the periodic table. It's gained an electron. So if it's in 5 of the periodic table, group 5 of the periodic table, it's got 5 electrons in its outer shell, gained 1. It's got 6 electrons in its outer shell. It's bonding 6F, so it's got 6 bonding pairs. I always put the minus in brackets. The brackets in this case doesn't denote concentration as it often does. In this case, it just means somewhere, somehow, there's a minus charge on here. It's almost like a wrapper around this to say somewhere there's a minus charge in this. It's gained a minus, it's gained an electron. So it's got 6 electrons in the outer shell, 6 bonding pairs, all repel equally, octahedral shape. If it was asking for the bond angle, it would be bond angle 90. H2F plus, so what's the F got? Well, that's F is in group 7. If it's a plus, it's lost an electron, so it's not got 7 in its outer shell now, it's got 6 in its outer shell. If it's got 6 electrons in its outer shell, 2 are involved in bonding pairs, it puts an electron in each of these covalent bonds. So 2 bonding pairs, it had 6 in its outer shell, 2 bonding pairs, it's got 4 left over, it's got 2 lone pairs. So that's how we draw it. Again, the plus charge, I put square brackets around to say that there's a plus charge somewhere on this molecule. How are they going to repel? Well, the 2 bonding pairs repel most to the greatest extent, and then the bonding pair, so the 2 lone pairs repel greatly to the greatest extent. The lone pair to bonding pair repels to the next greatest extent, and then to the least greatest extent the 2 bonding pairs repel. So these 2 bonding pairs get pushed closer together. Normally, if it were 1, 2, 3, 4, a tetrahedral shape, it would be a bond angle of 109.5. Every time we replace a lone pair with a bonding pair, the bond angle goes down by 2.5. So if it's 1 lone pair and 3 bonding pairs, it comes down from 109.5 down to 107. 2 lone pairs comes down by 2.5 again down to 104.5. And you actually, although the lone pairs influence the shape, you actually don't use those to name the shape. You only name the shape according to what you see, i.e. the atoms, and we can see 3 atoms here, and it's in a bent shape or a V shape, whichever you prefer. Hydrogen fluoride with ethine, so that's C2H2, we've got the equation here with 2HF, makes this chemical here. It's called 1,1-difluoroethane, and the enthalpy change is minus 179 for this. So mean bond enthalpy, use the data in here to determine the bond enthalpy of a CF. So it's these 2 that we don't know here. So what we do is we do the bond enthalpy, which is minus 179, equals the bond enthalpy of the reactants, that's anything on the left, minus the bond enthalpy of the products, anything on the right. So what have I got? I've got 2 C2H bonds on the left in my reactant, so minus 179 is 2 C2H bond, 1 C to C, that's a triple bond, plus 2 HFs, take away, so subtract the bond enthalpy of the products, say take away 4 C2H bonds, I've got 4 of those, 1, 2, 3, 4, and 2, take away again, because it's a product, take away 2 C to F bonds. So let's put the numbers in then now. So we put the numbers in. A C2H bond is a 412 plus. They're all plus values because they all involve endothermic reactions, putting energy in to break the bonds. So they're all always plus values for the mean bond enthalpy. Plus 837, so that's the energy required to break a carbon-to-carbon triple bond. 2 HFs are 2 562s. Take away, subtract 348 for a carbon-to-carbon. So we've got a carbon-to-carbon bond. I should have put that in there really. I've missed the carbon-to-carbon bond in this top line here. But there's minus 348 for a carbon-to-carbon bond to break that one in there. 4 412s. 4 carbon to hydrogens, and then minus the 2 carbon to fluorine bonds that we don't know of. That's what we're trying to find out. Put all the numbers in, take them across to the other side. So minus 968, when you take all these numbers across to the other side, equals minus 2 times the carbon to fluorine bonds. Reverse the sign on both sides. 968 is twice the enthalpy required to break the carbon to fluorine bond. So divide by 2, 484. Got to be a plus value, as I say, because bond enthalpies always require energy. The endothermic reactions with plus delta H values require energy to break the bond. Question 2, we've got time of flight mass spectrometry is an important analytical technique. We've got a mixture of 3 compounds analysed, and we've got the formula of each of the 3 compounds. First of all, describe how the molecules are ionized during electrospray ionization. So there's 2 kinds of ionization. There's one where you just use electron impact, use an electron gun. It just removes an electron physically. Or electrospray is a bit more of a gentle technique, usually used for large molecules that you're afraid might get broken up or fragmented. And what you do first of all, you take the liquid sample and dissolve it in a volatile solvent. A volatile solvent is one that's got a low boiling point, something like water or methanol. It helps if it's purified at first and if it's polar, the solvent that you're dissolving it in, that is something maybe like water or methanol that's got delta plus and delta minuses. Polar bonds and hydrogen bonding, but you get the marks saying the liquid sample is dissolved in a volatile solvent or a solvent with a low boiling point, and then the solution is injected into the mass spectrometer through a capillary needle. Capillary needle is a needle with a hole going right the way through it. You get the marks actually for just saying a needle, and a high voltage applied. It's actually applied to the end of the needle, but a high voltage applied as the solution is injected through a needle will get you the marks. And then importantly, you need to say each particle coming out, it comes out as a very fine mist incidentally, gains a proton or an H plus ion. Give the formula of the ion that reaches the detector first in the time-flight mass spectrometer. Well, it's going to be this one. It's going to be the lightest one. The lightest ones travel the fastest. I'm going to hit the detector first, C3H5O2N. But remember, it's gained a proton. It's gained an H+, so it's now C3H6O2N with a plus. The sample of a germanium is analysed in a time-flight mass spectrometer using electron impact. So this is what I mentioned before. Electron impact is just removal of an electron. So it's germanium. It's got to be a gas and goes to Ge plus gas and electron. In other words, it's the first ionization energy of germanium. So all electron impact ionization is you have something called electron gun, which fires high energy electrons across the tube, and those electrons hit this molecule and just knock off another electron and form a Ge+. But the problem with that is it can fragment big molecules. But for something small and atomic like this, that's not going to be a problem. But nowadays, electrospray ionization is usually used. In the time-flight mass spectrometer, germanium ion reaches the detector in 4.654 times 10 to the minus 6 seconds. So I've got the time, I've got the kinetic energy, I've got an equation. Kinetic energy is half mv squared as well. So from the kinetic energy, maybe I can work out mass or velocity. The length of the flight tube is 96 centimeters. That's an issue because it should be in meters. So I'm going to have to convert that into meters by dividing by 100 and turn it into 0.96 meters. I've got the mass. No, it just tells me that the mass. I've not got the mass. I've got Avogadro's constant, so the number of particles in a mole. Let's see what we can do then. I know that kinetic energy is half mv squared, so let's start with that because I've got a value for half mv squared. It's 2.438 times 10 to the minus 15. So let's multiply both sides and get rid of that half. Multiply both sides by 2. So 4.876 times 10 to the minus 15 is mv squared. I can't do much else with that because I've not got the mass and I've not got the velocity, so we'll just leave that there for now. Length or distance of the tube is 96 centimeters. If I divide by 100, I turn centimeters into meters. So let's divide by 100, 0.96 meters. So this tube's got to be in meters. It's very nearly a meter, 0.96 meters. Now this is something that you need to remember. Velocity is distance over time. Think about the velocity of a car going at 30 miles per hour. 30 miles per hour. 30 miles. Miles is a distance. Hour, time. Per means divide by. Miles, distance, divided by per hour. Distance divided by time. That's the way to remember that because you're not always given it. The distance is 0.96 meters. We've got that into meters now. We've got the time. You've been given the time here. It's got to be in seconds, and it is in seconds, so I don't need to do anything with that. 206.274 is the velocity. It's going very quickly. So v squared, if I'm going to substitute in here, I can square it. 4.25 times 10 to the power of 10. Now then, I've got this. 4.876 times 10 to the minus 15 is mv squared. I've just worked out v squared, so I can substitute v squared in there, and I can rearrange it. So 4.876 times 10 to the minus 15 divided by 4.25 times 10 to the power of 10 is going to be the mass, and it gives me the mass in kilograms. It says here, it helps me out here, mass is in kilograms, so I've got it in kilograms. Now then, I can work it. That's for one particle, by the way. This is the mass of one particle. We're only talking about one particle going down the tube. So if I multiply by Avogadro's number, 6.022 times 10 to the power 23, I'll work out the mass of 1 mole of particles. It's in kilograms, however, so to get kilograms down into a lower unit value of grams, taking kilograms a larger unit value down into a lower value, then I'm going to multiply by 1,000, so 6.91 times 10 to the minus 2 multiplied by 1,000 to get down into grams is 69.1. And it should be a whole number. Use the information to calculate the mass in grams of 1 mole of these germanium ions. Use your answer to state the mass number. So the mass numbers are always in whole numbers. So let's scale it up to 69, and that is your answer. If it's an ion, if it's a plus ion, it's lost an electron during electron impact, and an electron has got a negligible value, so it's not going to change that number by very much. So 69 as a whole number. Question 3. Questions about chromium and its compound. Complete the full electron configuration of a chromium atom. So first of all, you've got to find out the mass, the atomic number or the proton number of a chromium atom. And it's 24. So if you look on a periodic table, it's 24. Now you might think that the 4s electrons go in before the 3d. First of all, that's the first thing to know. So you might go 2s2, 2p6, 3s2, so that's standard, and then 3p6, and then you might put 4s2, 3d4. But what a chromium atom does is it half fills the 4s and half fills 3d to become stable. So it takes, instead of 4s2, 3d4, it goes 4s1, uses one of those electrons to half fill the 3d level. Copper does the same and goes 4s1, 3d10, incidentally, to fully fill the 3d level. So a 3d level will become half full or fully full and will take an electron from the 4s to increase its stability. An atom has 2 more protons and 3 more neutrons, an atom of 52 Cr. So 52 Cr, if you actually look up chromium, again I've said it's got 24 protons, so it's got an atomic number or a proton number of 24. So it's got 24 protons if you look it up in the periodic table. Here, by subtraction, 52 take away 24 will give you the number of neutrons, so it's got 28 neutrons. Now it says, deduce the symbol of an atom that's got 2 more protons. So instead of 24, it's now got 26, and 3 more neutrons instead of 28. It's got 31. 31 add 26 is 57. So it's 5726 Fe. Sample of chromium contains 4 isotopes, relative atomic mass 52.09. Table shows the mass number and percentage abundance of 3 of these isotopes. So there's 4 isotopes and it shows 3, so there's 1 missing. So you've got the percentage abundance, which is how much there is, how common it is. So the 4th one, so we could add up these and subtract from 100 to work out that there's 3.6% that's missing. So that must be the abundance of the missing isotope. So it's 2.8, add 10.9, add 2.7, subtract from 100 gives 3.6%. Now it's asking for, after the percentage abundance, show by calculation the mass number of this isotope is 50. So we've got to prove that it's 50. Okay, so let's first of all imagine that we had 100 particles, 100 atoms. 82.8%, 82.8 particles out of the 100 have a mass number of 52, 10.9 out of the 100 have a mass number of 53, 2.7 out of the 100 have a mass number of 54, and 3.6% out of the 100 have a mass number that I don't know. I'll call that mass Y. So this is the number of particles out of the 100 that I've got mass 52. So if I multiply those two together, I'll find out the mass of these particles. Multiply 10.9 particles multiplied by a mass of 53 will work out the mass of these particles. 2.7 multiplied by a mass number of 54 will work out the mass of these particles. And I've got 3.6 particles of unknown mass Y. So my total mass, when I put it all together, and it tells me what my So my total mass is 5029.1 at 3.6y, where y is the mass of this unknown particle. Now, what's an average? An average is the total mass, I've worked that out, 5029.1 at 36y, divided by the number of particles. The number of particles is 100 because I've decided that. So 5029.1 at 3.6y divided by 100 equals the average. And we're given the average in there, 52.09. So now if I multiply both sides by 100, 5209 equals 5029.1 at 36y. Take the 5029 to the other side. 179.9 is 3.6y. Divide both sides by 3.6, and so I've now got y, which is the mass of the unknown particle, 49.97. Now mass number's got to be a whole number, so I'll round it up to 50 to two significant figures. Deduce the oxidation state of chromium in Cr2O7. Well, the oxidation state of an oxygen is -2, 7 minus 2 is -14, and there's 2 minuses left over. So the two Crs must be +12, because +12 take away -14 leaves 2 minus over. If the two Crs are +12, 2 Crs +12, each Cr must be +6. Iodide ions can be oxidized to iodine using Cr2O72- ions. Deduce a half equation so that the oxidation of iodide ions, they're I- to iodine. Now remember, iodine is I2. The halogens pair up in twos and form a covalent bond between each of their atoms to fill up their outer shells. So in group 7, so they need to gain 1, so they put 1 in each two. Each atom puts 1 electron in each into a covalent bond, so forms I2. So we need 2 I minuses, and then a half equation has always got electrons. Well, there's 2 minuses on the left hand side, so I need to introduce 2 E minuses on the right hand side to balance the electrons. Deduce a half equation for the conversion in acidic solution. That's important. Acids produce H pluses, so we're going to need some H pluses of Cr2O7 ions to Cr3+. You'll see the problem. If I've not got H pluses, I've got Cr2O72- going to Cr3+. Where would the oxygens go? They've got to go somewhere. So it tells me in the equation that Cr2O72- make Cr3+. So where do these oxygens go? And that's why you need H+. So when you're balancing half equations, you're always allowed to put H pluses in there, and you're always allowed to make water. They're two things that you're allowed to always introduce. And it gives you a clue by saying acidic solution here anyway. So I've put H pluses in, made Cr3+, and I've made some waters. Now let's have a look. Balancing it. 2 Crs, so 2 Crs there, 7 Os, 7 waters. That creates 14 H's. I need 14 H pluses. What have I got? Got 2 minus and 14 plus, so that gives me 12 plus on this side. I've got 6 plus on that side, so I need 6 electrons on the left hand side. Now I've got 6 pluses on each side. Use your answers from 3.5 and 3.6 to deduce the overall redox equation. So what I do is I take everything from the left, oh no, I don't. First of all, I've got to balance the electrons. I've got two electrons in this one, and I've got 6 electrons in this one. I've got to get equal numbers of electrons so I can cancel electrons. In my overall equation, I can't have any electrons, so the number of electrons have got to balance. So I've got to multiply everything through by 3. So 3 times 2I minus is 6I minus. 1I2 is 3I2 and makes 6 electrons. Then I add everything up on the left. So once I've multiplied this top one by 3, I've got 6I minuses on the left here. Anything else on the left in my other equation, because I'm adding this on as well? Cr2O7 2 minus 14H plus and 6 electrons. And on the right hand side I've multiplied this by 3, remember, so I've got 3I2, 6 electrons, 2 Cr3 pluses and 7 waters. Now my electrons will cancel, and when my electrons cancel I end up with 6I minus Cr2O72 minus 14H plus makes 3I2, 2 Cr3 pluses and 7 waters. Question 4. The first ionization energies of the elements in period 2 change as the atomic number increases. Explain the pattern in the first ionization energies as you go across the period 2 from left to right, from lithium across to neon. So first of all, you've got to say, as you go left to right, the first ionization energy usually increases. And this is because the atoms get more protons as you go across, and therefore you get an increased nuclear charge. It's important to put the words nuclear charge. If you don't put the words nuclear charge, you lose marks. Nuclear charge. So therefore there's a greater attraction from the nucleus for the outer electrons. Again, outer electrons is an important thing to put, because it's the outer electrons that are being removed when you have a first ionization energy. So really important to put nuclear charge and outer electrons. All the atoms across the period have the same number of energy levels, so the same amount of electron shielding. So when you get inner energy levels, then they reduce the attraction from the nucleus to the outer electrons. But in this case, because you're going across the period, they have the same number of energy levels, so the same amount of shielding. That gets you a mark. Now we're going to mention the two anomalies. As you go beryllium across to boron, one across, actually the first ionization energy comes down. So boron's first ionization energy is lower than beryllium. And the reason for that is because boron has got a 2p1 and a 2p1 electron. It's got a p electron. Beryllium only had one s2, two s2. And that p electron's further from the nucleus. It's got more energy than the 2s, and having more energy, therefore it's already got some energy, more energy than the 2s, and therefore you need to put less energy in to remove it. So if you say that boron's got a lower first ionization energy than beryllium because it's got a 2p electron further from the nucleus with more energy than the 2s electron, the outer electron in beryllium rather, you'll get the mark. Oxygen again. Oxygen's got a lower first ionization energy than nitrogen. So nitrogen, you had nitrogen and oxygen. You'd expect oxygen to be higher, but it's lower. And the reason is it's got 2p4. Normally what happens is in the p levels, you go 2p1, 2p2 and 2p3. It can hold 6, but when you get to, so it's half full at 2p3. When you get to the fourth electron, then they pair up. So one of the other p electrons has got to pair up with this fourth electron. And when you get a pair of electrons, in other words, you get 2p4, they repel each other. And when they repel each other, they need less energy to be removed during the first ionization energy compared to non-paired electrons, that is if it's 2p1, 2 or 2p3, where they've then not got to pair up. Question 5. Nitrogen monoxide reacts with chlorine to form nitrosyl chloride, NOCl, and I've got an equilibrium reaction here. 1.5 moles of NO are mixed with 1 mole of Cl2, and the mixture is left to reach equilibrium. So when I mix the two reactants on the left, I actually haven't got any products on the right initially. So I haven't got any of this NOCl made at all. But then in the equilibrium mixture, it tells me I've got 0.350 moles of NOCl. Calculate the number of moles of NO and Cl in the equilibrium mixture. So once dynamic equilibrium's reached. I always set this out as a table. I can see it more easily in a table, so I suggest you do too. So let's put the three chemicals, the two reactants, the NO and the Cl2, and then the product, the NOCl. And then let's say how much we've got at the start. So at the start we've got 1.5 moles of NO. It tells me that I've got 1 mole of Cl2 and I've got no moles of NOCl. No surprise, because I've not made any yet. I've not mixed them yet. So when I mix them and I wait for equilibrium to be reached, remember that's the point where the concentrations of the reactants and the products no longer change and the forward and backward reaction are going at equal rates. Then it tells me that I've got 0.35 moles of NOCl. Well, I can look at my molar ratios here in my equation to see if I've made 0.35 moles of NOCl, 2 moles of NO would react with 1 mole of Cl2 to make 2 moles of NOCl2. That's a molar ratio 2 to 1 to 2. So the number of moles of NO used up equal the number of moles of NOCl made. So I've used up 0.35 moles of NO to make 0.35 moles of NOCl, because there's a number 2 there and a number 2 there, the equal number of molar ratios. The number of moles of Cl2 is only 1. So I've used half the amount of Cl2 that I have of NO, so I've used half the amount of this, so it's 0.35 divided by 2. I've used up 0.175 moles of Cl2 in my molar ratios. Now, this is how much I started with. I've used up 0.35. Remember, this is a reactant reacting away to make the product, the NaCl. So if I subtract these two, I've now got left over 1.15. Same for Cl2. I started off with 1 mole. I've used up 0.175, so I've got 0.825 moles left over, and I've made 0.35 moles. I didn't have any to start with. I've made 0.35 moles, so I've now got 0.35 moles. Give the expression the equilibrium constant Kc for the reaction between nitrogen monoxide and chlorine to form nitrosol chloride. So what I do is I take the concentrations of the reactants, of the products NaCl, and I raise it to the power of 2, that's the number of front, divide by NO, that's one of the reactants, raised to the power 2, divided by Cl2 to the power of 1, because there's a 1 in front of the Cl2. So it's NoCl2. Concentrations, remember, are in square brackets. NoCl2 in square brackets raised to the power 2 divided by NO in square brackets to the power 2, Cl2 to the power 1, because there's only a 1 in front of the Cl2. A different equilibrium mixture is prepared in a flask of 800 centimetre cubed. Remember, 800 centimetre cubed is 0.8 decimetre cubed. 10 centimetre cubed up into a higher unit value of decimetre cubed, I divide by 1000, 0.8 decimetre cubed. That'll be important in a moment. At equilibrium, this mixture contains 0.85 moles of NO and 0.458 moles of Cl2. For the reaction, the temperature, at this temperature, Kc is 1.32 times 10 to the minus 2. So the reason Kc is changed is because the temperature has changed. The equilibrium constant would stay the same if the temperature stays the same. So Kc only changes if you change temperature, but we have changed temperature, so that's why Kc has changed. Determine the amount of moles of NaCl in this equilibrium mixture. So my expression for my equilibrium is still the same for my equilibrium constant, but the equilibrium constant has changed to 1.32 times 10 to the minus 2. Still equals NaCl concentration to the power 2 divided by NO2 concentration to the power 2 divided by the concentration of Cl2. What have I been given? It contains 0.85 moles. So concentration is moles divided by volume, 0.85 divided by a volume. Volume is in decimetre cubed, because concentration is moles divided by volume in decimetre cubed. So to turn centimetre cubed up into decimetre cubed, a larger unit value, I divide by 1000, 0.8. So NO's concentration is 0.85 divided by 0.8, still to the power 2 here for my expression, and this one 0.458 moles of Cl2 divided by 0.8 again, so that's the number of the concentration is number of moles divided by volume, and they're in the same flask, so 0.8 is my volume. So I can work these out. 0.85 divided by 8 squared, 0.45 divided by 8, and multiply those. So when I rearrange the equation, then these are on the bottom on the right hand side, they get to the top on the left hand side. So 1.32 times 10 to the minus 2 multiplied by 0.85 divided by 8 squared multiplied by 0.45 divided by 8 comes out as 8.53 times 10 to the minus 3 is the concentration of NaCl squared. Square root both sides, so NaCl concentration is now equal to 0.0924. Number of moles is concentration times volume, so I've got the concentration, I've got the volume, which is 0.8 because they're in the same flask. 0.0924 multiplied by 8 is 0.0739. Have a look at my other values: 3 significant figures, 3 significant figures, 3 significant figures, 3 significant figures. Everything's to 3 significant figures, so I can put that as 0.0739 to 3 significant figures. Question 6. A student does an investigation to determine the relative formula mass, MR, of a solid unknown diprotic acid, H2A. A diprotic acid is an acid that when you react 1 mole of the acid, it reacts with 2 moles of the base or the alkali, the sodium hydroxide. So my molar ratio is 1 to 2. So diprotic acid actually releases two H pluses. The H pluses are the component part that reacts with the sodium hydroxide. But anyway, for now, we'll just say one acid reacts with two base. That's what a diprotic acid does. I've got 250 centimetre cubed of the acid, and in there I've got 1,300 milligrams of H2A. Remember, milligrams, I don't usually use milligrams. I want to get into grams, and to get milligrams up into grams into a higher unit value, I divide by 1,000. So that's 1.3 grams. I must remember that 250 centimetre cubed has got 1.3 grams of the diprotic acid. A pipette is used to 25 centimetres cubed of 0.0112 decimeter cubed sodium hydroxide to a conical flask. I've been given a volume, since centimeter cubed needs to be in decimeter cubed, but I've been given a volume and a concentration. Concentration is moles divided by volume in decimeter cubed. I can work out the number of moles of sodium hydroxide. That's the only reason that they've been giving me a volume and a concentration here. And then I've got some results from my titration that I'll come to in a minute. I'm going to do something immediately with this 25 centimeter cube, this volume and this concentration, because concentration is 0.112. 25 centimeter cube, get that into decimeter cubed. Centimeter cubed up into decimeter cubed, you divide by 1,000, 0.025 decimeter cubed, and concentration is moles divided by volume, so 0.112 is moles divided by 0.025, multiply both sides by 0.025. I've got the number of moles of sodium hydroxide, 0.0028. The reason I did that first is because this stands out to me that I've been given a volume and a concentration, so it'll want me to work out moles. The next thing, why has it given me, why have I been given an equation here? Well, I've been told it's a diprotic acid. 1 mole of acid reacts with 2 moles of sodium hydroxide or a base. And the simple answer is, it wants me to work out the number of moles of sodium hydroxide, by of the acid, by dividing the number of moles of sodium hydroxide by 2. So the number of moles of my diprotic acid, my H2A, is 0.0028, the number of moles of sodium hydroxide divided by 2, 0.0014. Now, I've used all the information in that table that I can. I've now got to come to these. This is my titration. This is the amount of acid that I've added, and I've got to look for two concordant results. Two concordant results are my titration, the amount that I've added, has got to be no more than 0.1 apart. So I'm looking for two results that are no more than 0.1 centimetre cubed apart. So I'm looking at titration 1 and titration 5. 26.40 and 26.50. Yes, those are no more than 0.1 apart. Titration 2 is quite a bit out, and the rough one's way out. So I'm going to ignore the rough one and ignore titration 2. I just use the results of the two titrations that are concordant, no more than 0.1 apart. So if I take these two results, 26.40, add 26.50 and I divide by 2, I'll get the average amount. So I've now got the average. 26.45 centimetre cubed is the average amount of acid I've needed to add to this amount of sodium hydroxide. Now then, it's in centimetres cubed, so I now know that there's 0.0014 moles of acid in 26.45 centimetre cubed. I want to know the number of moles that are in this 250 centimetres cubed, because I've got a mass of the acid in this 250 centimetre cubed. If I can get the number of moles in this 250 centimetre cubed, I can work out MR. So I've got 0.0014 moles in 26.45 centimetre cubed. If I divide by 26.45 centimetre cubed, I work out the number of moles that's in 1 centimetre cubed. Multiplied by 250 gives me the number of moles in this 250 centimetre cubed. 0.0132 is the number of moles of solution of this acid in the that I've started with, and I know that there's 1.3 grams of this acid. So moles is mass divided by MR. Moles 0.0132 is the number of moles in this 250 centimetre cubed. There's 1.3 grams in this 250 centimetre cubed divided by MR. So rearrange 1.3 divided by 0.0132 is 98.5. I'm going to put it to 3 significant figures because everything else is to 3 significant figures. My actual mass is to 4 significant figures, but I'll go with the lowest piece of data in terms of significant figures. These piece of data have got 3 significant figures. This has got 4, so I'll go with 3 significant figures because that's my lowest piece of data in terms of significant figures, and I've got to match that. 98.5. The uncertainty in the pipette in this experiment is 0.06 centimetre cubed. Now, a pipette only uses one reading. You only read once off the pipette, so I've not got to multiply that value by anything. So you multiply this value, this percentage error, by the number of readings that you have. But since the pipette only has one reading, it's 1 times this. So this is just as it is. Calculate the percentage impurity in this pipette. So it's 0.6. The error is should be 0.6, should be 0.06 actually, divided by 25. 25, where's the 25 come from? It's come from, 25 is the amount of sodium hydroxide that you put in the pipette. So it's 0.06 should say, divided by 25 is the volume that's been put in the pipette, multiplied by 100%, 0.24%. Before adding the solution from the burette in the rough titration, there was an air bubble below the tap. At the end of this titration, the air bubble was not there. Explain why this air bubble increases the final burette reading. Well, when you're pouring from the burette, some of it will fill the air bubble. So some of the solution replaces the air bubble before it actually comes out of the burette. So that's why the reading is higher than it should be, because some of the actual acid has actually filled the bubble where the burette is before anything's actually started to come out of the burette. So the solution, the acid, first replaces the air bubble before it's dispensed from the burette. During the titration, the student washed the inside of the conical flask with some distilled water. That's fine. Washing down the inside of the conical flask is actually good practice to make sure that all the sodium hydroxide is in the base of the flask and reacts. Why does washing not give an incorrect result? Well, there's two reasons that you can put there. You get 1 mark for saying it in different ways. One, the water doesn't react, so there's no problem adding water to it. And or the number of moles sodium hydroxide in the flask is unchanged. You've not removed any sodium hydroxide from there. So either of those two. The water does not react is probably the easiest answer to remember. Question 7.1. Magnesium is used in one of the stages in the extraction of titanium. Give an equation for the reaction between titanium 4 chloride and magnesium. State the role of magnesium in this reaction. It's a redox question. It's asking you about reduction and oxidation. First of all, you've got to work out what titanium 4 chloride is. So titanium, if it's in oxidation state 4, Cl always gains 1 electron. It's in group 7 of the periodic table. So most of the time it's in oxidation state -1 because it gains 1 electron. Not always, but it's a reasonable starting point. So that's in -1 oxidation state. 4 minuses, 4 minus 1 balances the +4. So the titanium's in +4 and Cl's are in -1. You're going to need 4 of them. Magnesium is Mg. It makes MgCl2. We know magnesium's in group 2, loses 2 electrons, +2 oxidation state. Cl -1, so 2 -1s to balance out the +2, so MgCl2. And it says it makes titanium. To extract titanium is to make titanium on its own, and you can need 2 Mgs to balance out the 4 Cls, which are on the left hand side. A mixture of magnesium oxide and magnesium hydroxide has a mass of 3,200 milligrams or 3.2 grams. The mixture is reacted with carbon monoxide in the following equations. Calculate the percentage by mass of magnesium oxide in this mixture. So first of all, my first clue here is that the mass of water produced is 210 milligrams, divided by 1,000, 0.21 grams. Oh, sorry, the role of the magnesium is a reducing agent. The magnesium has gone from 0 oxidation state up to +2. It's been oxidized. The titanium's gone down from 4 down to 0, so that's been reduced. This is a reducing agent. The magnesium's been oxidized and in turn has reduced the titanium. Back to this one then. So the mass of the MgO and the MgOH2 combined, it says, is 3,200 milligrams or 3.2 grams. But more importantly, the water here, I've got a mass of water produced 210 milligrams divided by 1,000, I've got 0.21 grams. So moles of water is mass divided by MR. I can work out the MR of water, which is an oxygen, which is 16 and 2 ones for the 2 hydrogens, 0.0116 moles of water. and my water is produced here. So if I've got 0.1167 moles of water here, I've got equal numbers, 1, 1, 1 and 1. When you balance it, I've got an equal number of moles of MgOH2 reacting to make this amount of water. So if I've made 0.01167 moles of water, I've used MgOH2, I've used the same amount of same number of moles of MgOH2. So number of moles is 0.1167 is mass divided by MR. I've worked out the MR of MgOH2. It's a magnesium which is 24, 2 16s for the 2 oxygens and 2 1s for the hydrogens. It's 58. Multiply both sides by 58. I've now worked out the mass of MgOH2 is 0.677 grams. Now I know the combined mass. It tells me the combined mass of the magnesium oxide and the magnesium hydroxide is 3.2 grams or 3,200 milligrams. So if I subtract the mass I've just worked out the magnesium hydroxide from this total mass, 3.2 grams taken by 0.677 grams is 2.523 grams. That must be the remaining magnesium hydroxide. So I've got 2.52 grams of magnesium hydroxide. The question's asking the percentage by mass of magnesium oxide in the mixture. So 2.523 grams of magnesium oxide in the total mass of the mixture, which is 3.2 grams, divided by 3.2 grams, multiplied by 100%, 78.8%. I've put it to 3 significant figures because 210 milligrams is to 3 significant figures. This is to 4 significant figures, but always take the lowest data value, lowest number of figures from the question, 3 significant figures, so my answers to 3 significant figures. Question 8, we've got some mixtures of compounds. We've got to distinguish between them by adding some reagents and say what we'd see. Sodium chloride and barium chloride. So the first clue is barium. Barium, if you make barium sulfate, it's a white solid. So you can make barium sulfate by adding sulfuric acid. Or make barium sulfate. Sodium sulfate that's made from sodium chloride is soluble. All sodium salts are soluble, so there's no visible change there. But with barium chloride you get a white solid or a white precipitate of barium sulfate. Sodium chloride and sodium carbonate, well, you've got 2 choices here. If you added acidified silver nitrate, the silver nitrate will make silver chloride as a white precipitate or a white solid here. Silver chloride. You could then add, if you weren't sure, you could add dilute ammonia, which would dissolve the silver chloride. And actually then with acidified silver nitrate, normally you get silver carbonate, but if you acidify it, it will dissolve the carbonate, the silver carbonate, and it'll actually react with some of the sodium carbonate and make bubbles. The other alternative, of course, is to add any named acid like hydrochloric acid or sulfuric acid. It's going to have no change with sodium chloride, but with a carbonate it will make bubbles. So either of those 2 solutions will get you the marks. Question 9. Which sample measured at room temperature and pressure contains the greatest number of particles? Well, the number of particles in a mole is 6.022 times 10 to the power 23 Avogadro's constant. So if I work out the number of moles, and every mole has the same number of particles, we can change the question around by saying, therefore, whichever one has the greatest number of moles will have the greatest number of particles. So let's work out the number of moles. So to work out moles is mass divided by MR. MR of hydrogen H2 is 2, so 1 divided by 2, 0.5 moles of hydrogen in answer A. Helium has got a mass number of 4. Helium atoms are in group 8 or group 0. They've got full outer shells. They don't bond with anything. They've got an MR of 4. So moles is 1 divided by 4, 0.25 moles. And now here you need to know at room temperature and pressure, any gas, doesn't matter whether it's hydrogen or helium, 24 decimeter cubed is 1 mole. So 1 decimeter cubed is 24th. 1 divided by 24th of a mole. It doesn't matter whether it's hydrogen, helium or any other gas. So your answer is A, has the largest number of moles and therefore the largest number of particles. 5 grams of an oxide of molybdenum contains 4 grams of molybdenum. So I can look up the MR of molybdenum, 95.95. I can work out the number of moles of molybdenum in this oxide. Mass divided by MR is 4 divided by 95.95, 0.042. I know that there's 1 gram of oxygen in this oxide because there's 5 grams of the oxide and 4 grams of molybdenum. So 1 gram of the oxide, moles is mass divided by mR, 1 divided by the mass of an oxygen atom is 16, 0.0625. So that's the ratio of molybdenum to oxygen. Divide by the small number, 0.042 divided by 0.42. I've got 1 molybdenum to a ratio of 0.0625 divided by 0.42 to 1.5 oxygen, 2 to 3, MO2O3, answer C. Question 11. Which substance has delocalized electrons? The answer to that is graphite, straight off. Graphite has delocalized electrons between the layers. That's what allows it to conduct electricity. Which species is not pyramidal in shape? Phosphorus is in group 5, so it's got 5 electrons in its outer shell. 3 bonding pairs, 1 lone pair, therefore, so it's going to be trigonal pyramid. H3O+, oxygen's in group 6, loses 1 electron to form a plus. Means there's 5 in its outer shell, 3 bonding pairs, 1 lone pair, again trigonal pyramid. CH3-, carbon's in group 4, gains 1 to get a minus charge, means it's got 5 electrons, 3 bonding pairs, 1 lone pair, again trigonal pyramid. Whereas BF3, boron's in group 3, 3 electrons in its outer shell, 3 bonding pairs with the 3 Fs. It's going to be trigonal planar with a bond angle of 60. Which change occurs when water is vaporized? Intermolecular forces are overcome. That's what happens when something changes state. You break the intermolecular bonds between the particles. Question 14. Which equation represents a reaction that has a standard enthalpy change equal to the standard enthalpy of formation of barium chloride? Enthalpy of formation means that you're making 1 mole of a substance from the elements as you'd find them in their standard states. That means as you'd normally find them in the laboratory, under laboratory conditions of temperature and pressure. So 100 kilopascals and 25 degrees C, or 273 Kelvin. So as you'd normally find them in their standard states. How would I normally find barium? Well, barium's a solid in group 2, it's a metal in group 2, so I'm looking for barium as a solid. Now C and D have got barium as solids, but there's only one element there, barium, Ba2+, is an ion, so my answer is automatically C. Let's just check. C is chlorine gas. Chlorine is a gas under normal laboratory conditions, and they're all making 1 mole of barium chloride as a solid anyway. So my answer is C. Which equation does not represent a redox, where there's reduction and oxidation going on? Well, magnesium there is an element on its own, so it's in oxidation state 0. Chlorines are in oxidation state -1 usually, so -1 and -1 is -2 for the 2 Cls. No charge left over, the Mg is in +2, so it's gone from 0 up to +2. It's been oxidized. There's some kind of redox going on there if the magnesium's been oxidized. CH4 add oxygen added. Adding oxygen is another way of oxidizing something or removing hydrogen. The carbon has been oxidized into CO2. Fe is an oxidation state 0 there as an element on its own. SO4 is a 2- ion. There's no charge overall, so the Fe must be in +2. It's gone from 0 to +2. It's been oxidized. So the answer must be D. Oxygen is in -2 oxidation state, no charge left overall, so the copper must be in +2 oxidation state there in copper 2 oxide. Here I've got Cl, 2Cl, 1- is in -1 oxidation state, no charge overall, so the copper's in +2. So it's gone from copper 2 oxide to copper 2 chloride. It's not changed its oxidation state. There's no redox going on there. The answer is D. Which property do you expect of the radium element radium? Radium is a metal at the bottom of group 2. As you go down group 1 and group 2, because the electrons are getting further away from the nucleus, then they're ionized more easily. The first ionization energy goes down as you go down a group. So therefore it's going to be very, very reactive. It's a very, very reactive metal. It forms a soluble sulfate. Now as you go down the group, they get more and more insoluble. It does not react with water. Yes, it's a metal, and most metals react with water. and so it will react with water, especially one so far down the bottom of group 2. It's a good conductor of electricity. Yes, it will conduct electricity, so all metals conduct electricity. It forms a covalent fluoride. No, it's right down the bottom of group 2, so it's going to want to lose these electrons very, very readily. It's got a very weak attraction for its outer electrons from the nucleus, so it's going to lose these electrons very, very readily. And with fluoride, that's right at the top of group 7, a small atom wanting to gain an electron with a very small size, so the outer electrons pulled in very, very tightly, very, very closely, very, very strongly to the nucleus. That's going to form an ionic fluoride. The radium's going to lose its electrons, and the fluoride is very much wanting to gain them. So forms an soluble sulfate. No, it's going to be insoluble. Does not react with water. Yes, it will react with water. Forms covalent fluoride. No, it's going to be an ionic fluoride. Is a good conductor of electricity. That is your answer. Answer C. Question 17. Which statement is not correct? A. Strontium has a lower first ionization energy than calcium. Well, strontium is below calcium in group 2, so it's got more electrons, more shells, electrons are further away from the nucleus, less nuclear attraction, more shielding, etc. So it's going to have a lower first ionization energy, so A is correct. Strontium has a larger ionic radius than calcium. Again, yes, larger. More electrons, more shells, further away from the nucleus, a larger radius. Strontium reacts less vigorously with water. Now, as you go down the group, you get more and more reactive, so strontium will react more vigorously. Remember, if it's losing electrons, they're going to be more easily lost if they're further away from the nucleus, with more shielding and lower nuclear attraction. So C is incorrect. D. Strontium hydroxide is more soluble in water than calcium hydroxide. No, that is correct. Strontium hydroxide is more soluble as you go further up the group than the hydroxides become less soluble. So strontium hydroxide is more soluble as you go down the group. So your answer is C is not correct. Which property of the group 2 elements, calcium down to barium, increases with atomic number? Straight off atomic radius, we've discussed that already. As you go down a group, more electrons, more shells. Which is the best oxidizing agent? So you've got to remember what an oxidizing agent is. An oxidizing agent causes reduction. Oil rig reduction is gain of electrons. So F2 readily forms F minus. So it's going from oxidation state 0 to -1. It's being reduced. Therefore, it's causing something else to be oxidized. It's a very good oxidizing agent. Your answer is A. Some fuel in the spirit burner is burned and the heat produced is used to heat a container of water. So this is delta H equals minus MC delta T. What is the amount of energy absorbed by the water? So you just remove the minus. So that's exothermic. Now we're talking about an endothermic reaction where heat is absorbed. So enthalpy heat absorbed is MC delta T, sometimes called Q. So it says here that the heat rise is Y. So if I substitute delta T, temperature change for Y, then I get MCY. My answer is A. The equation below represents the complete combustion of butane. 20 centimetre cubed of butane are burned in 0.2 decimetre cubed of oxygen, in other words 200 centimetre cubed. Which statement is correct? All volumes are measured at the same temperature and pressure. Let's work it out then. So for gases, the ratios of volumes reacting, the ratios of moles reacting, because whatever gas you've got, 24 decimetre cubed is 1 mole. So you can turn ratios of moles reacting into ratios of volumes reacting. So I could say that 1 to 6.5 makes 4 and makes 5. I could talk about moles, or I could talk about volumes in terms of ratios reacting here, as long as they're all gases. 20 centimetre cubed of butane are completely burned in 0.2 decimetre cubed of oxygen. Which statement is correct? So 20 centimetre cubed of butane would react with 6.5 times the volume of oxygen. So 6.5 times 20 is 130 volume of oxygen. So I'm going to react with 130 centimetre cubed of oxygen. So now then, I've got 0.2 decimetre cubed of oxygen, or 200 centimetre cubed of oxygen. I'm going to react at 130 centimetre cubed of it. I've got 70 centimetre cubed of oxygen remain. The answer is C. Question 22. Which statement is correct about reactions involving halide ions? So sodium chloride reacts with chlorine when, forms chlorine when added to concentrated sulfuric acid. No, it's going to make hydrochloric acid gas as white steamy fumes. Sodium chloride forms chlorine when added to bromine. No, there's going to be no reaction because chloride ion cannot be displaced by bromine. Bromine is less reactive than chlorine. C. Sodium bromide forms bromine when added to concentrated sulfuric acid. Yes, it will act as an oxidizing agent, sulfuric acid, and actually make bromine, so C is correct. Sodium bromide forms bromine when added to iodine. No, you're not going to get a displacement reaction. Iodine is less reactive than bromine, so your answer is C. What's the percentage yield when 20 grams of aluminium is produced from 50 grams of aluminium oxide? So if I look at 50 grams of aluminium oxide, I will work out the MR. Aluminium is 27, so 2 27s and 3 16s is an MR of 102. Moles is mass, 50 grams divided by the 102, 0.49 moles of aluminium oxide. 2 moles makes 4, so twice as much aluminium, twice as many moles of aluminium are going to be produced. So I multiply the 0.49 by 2 and I work out that I've got 0.98 moles of aluminium being made. I'm going to turn that into grams, so moles is mass divided by MR, 0.98 moles of aluminium is the mass divided by the MR of aluminium, which is 27. 0.98 times 27, I'm going to make 26.46 grams of aluminium. That's my theoretical, that's what I should make. So my percentage yield then is 20, that's what I did make, divided by my theoretical yield, 26.46, multiplied by 100%, 75.6%, 76% if you round it up. The answer is A.